Section 2.3 is going to continue our discussion of derivatives. And what we did in 2.2 was called basic limits, or basic derivatives. So we used some very simple kinds of processes rules. And everything worked kind of the way we would expect it to work. That's about to change. Things are not going to work the way we would expect them to work necessarily when we work with products and quotients. So the first one that we're going to take a look at is the product rule. And the product rule, the question we're asking ourselves is whether or not this works. Does the product of f times g's derivative just take the product of the first one times the product of the second one? That's what we'd like it to be. That seems like what it would intuitively be, right? Like the sums and the difference ones that we did in last section. So we're going to explore that possibility using a specific example. There's nothing special about this example except that it's easy to work with. We have f of x equal to 4x to the 9th and g of x equal to x cubed. So if we have the ability to do this, then what we're going to do is we're going to multiply, like this process on the first one here says we're going to multiply the two functions together and then take their derivative. So my two functions are 4x to the 9th times x cubed. And I'm going to take a derivative after I multiply them. So first we're going to multiply. So what's 4x to the 9th times x cubed? Good, 4x to the 12th. And then from what we did before, the simple derivative, right, of 4x to the 12th would be what? Fabulous, 48x to the 11th. And this is really the derivative of this product because we did the product first and then we did the derivative. Okay? What we're going to do down here is we're going to take the individual derivatives of f of x and g of x. And then we're going to find their product, and we're going to see how that lines up with what we just did, which should be the answer I'm getting. So what is the derivative of 4x to the 9th? 36x to the 8th. And what is the derivative of x to the 12th? I'm sorry, x to the 3rd. Thank you, 3x squared. And then if we multiply these together, yeah, you don't get what we just got, right? You don't. In particular, what you do get is 108 x to the 10th. But more, importantly than what it actually is that you get, it's not the same thing. It just isn't. So it does not work the way we would expect it to, right? Limits did this. I had the ability to do this with limits. Products and sums and differences, like we did in the last section, did this for derivatives even, and that worked. But it doesn't work for derivatives with products. So instead, we have a product rule that will work. So this product rule says that we're going to take the original function, f of x, we're going to multiply it by the derivative of g of x, and then we're going to do the reverse. We're going to take the derivative of f of x and multiply it by the original of g of x, and then we're going to add those two values together. And I'd at least like to justify that it's reasonable from the last problem, since I showed you why doing it the way we intuitively would have thought it worked didn't work. So we're going to use that same example that we had before right here. 4x to the 9th and x cubed. And we're going to do this way and see how it works. Okay, we're going to see that it really does, in fact, equal 48x to the 11th. Okay, so the first thing we do, I'll do this in a piece at a time. The first thing that we do is we rewrite the f of x function just as is, 4x to the 9th. The book will present it differently. The book actually takes this piece and it flips them. If you've taken a calculus class before and that's the order you're used to doing it in, great, I don't care. It doesn't make any difference because we can add things in backwards orders and we get the same value. It's called the commutative property. I like to do it in this order, and the reason I do is because you can always start. I don't have to actually do anything except for rewrite the first piece. So I've got a process by which I can move forward at least a little bit, even if I get stuck after that. Now the derivative of g of x, the derivative of x cubed is 3x squared, good. Now we're going to go in the other order. What's the derivative of 4x to the 9th? 36, whoops, forgot my 6. 36x to the 8th. And then g of x just gets rewritten x to the 3rd. Okay, so far so good? So those are the pieces. Now, generally speaking, this is sort of a pointless thing to do on this particular problem, what we're doing right now, using the product rule. The reason it is because it was really easy to just do the product and then find the derivative. Like that was super simple. There's no reason to use the product rule here. However, it is not always the case that we can combine things like this inside and then take their derivative. Sometimes we can't do that. So while I'm showing you that it works here, I'm doing it for a problem that is sort of silly to do it with. Does that make sense? Okay, so let's actually take a look at this. If I have 4 times 3, it's 12. X to the 9th and x squared is x to the 11th. And over here I have 36, x to the 11th. And what is 12x to the 11th plus 36x to the 11th? 48x to the 11th. Right, and it checks out. That's what it's supposed to be. Because that's what it is when I multiplied the two functions together and then found their derivative. So this is our product rule. This is what we're going to be using, whether we can or can't basically be able to simplify in the inside. So, or with the product. So this is an example of one where we could actually do this one and we could multiply it out and you could simplify it. In fact, you may have had some problems kind of similar to this on your homework in section 2.2. I think you did, in fact. Right? So it's not necessary for us to do that on this problem. But I want to show you what happens and that it actually works out again. I don't want you to feel like she just used a special case scenario and it worked out really nice, but how do I know that it works on everything? Well, I'm going to show you at least one more that it really works out on. So we're going to do the process that we just learned, and then we're going to go back and verify that it's really true by what we did in 2.2. So this process says I rewrite the first piece exactly like it is. Fabulous, I can do that. And then it says I'm going to take the derivative of the second piece. So what is the derivative of x squared minus 5? 2x. Lovely. There's addition inside of the product rule, so we're going to put a plus next. And now we're going to reverse that process. Now I need the derivative of the first piece. So what's the derivative of x squared plus 3? 2x. And I rewrite the second piece, x squared minus 5. Okay, so let's say we're doing the derivative gateway next Friday. You could stop right there. Would not expect you to do anything else, even though this cleans up and we're going to do it right now real quick. But you wouldn't do that next Friday on that particular gateway, okay? So as we clean this up, and the reason for doing so is because it's easy. That's one reason. When the cleanup is able to be done, we're simply going to do it. So we're going to distribute our 2x. So now I have 2x cubed plus 6x, right? And then we're going to distribute over here our 2x. And I have another 2x cubed. And then minus 10x. Does that look okay? Combining like terms, what do we get? Right, 4x cubed minus 4x. Okay, everybody good with that? Okay, so this is using the product rule. If we were doing this the way that we did back in section 2.2, we would actually multiply those together first. So we would FOIL this out, right? We'd multiply these two binomials together. That would be x to the 4th. In the inner term, we have a 3. In the outer term, we have a negative 5. So that's negative 2x squared. And my last term is negative 15. And then we would take its derivative. And sure enough, there's that 4x cubed minus 4x showing back up.
You don't want us to factor out the 4x?
We're not asking for it to be in factored form when we're done. There's no purpose in having it in factored form when it's done. Okay? So you've seen two examples of things where you can clean them up. I mean, quite a bit really at the end, right? So let me show you an example where the product rule is absolutely crucial now. There is no way to simplify x cubed cosine x. I can't. I mean, like, it's not even an option, right? It was an option on the last two examples I did. I kind of got to make a pick, and I showed you that it didn't matter which way you picked, whether to simplify it first or to take the derivatives first and then simplify. But on this one, we don't have a choice in the matter. Okay, so this is an example of where the product rule is crucial. It's necessary, only an option. So we're going to take our derivative. Tell me what the product rule says I'll do first. X cubed. Then what? Yeah, the derivative of cosine x, which many of you are saying is negative sine x. And if you don't want to put the negative there, you can put it on in front of the x cubed. That's fine. We'll put it there in a minute anyway. Now what? Okay, the derivative of x cubed is 3x squared and cosine x. There's not a lot of cleanup on this one to do. And that's actually kind of nice, because as I'm looking at this, the only thing to do, and you may have even done it in the process of doing the problem to begin with, is to simply move the negative in front of the x cubed. Negative x cubed sine x plus 3x squared cosine x. And the parentheses are no longer necessary because there's no simplification that needs to be done with them. And I have my solution. Okay, any questions so far? Okay, so that's the product rule. The quotient rule. Okay, so again, we're going to play with the values. We're going to use the same functions that we did before, actually, for f and g. And we're going to see whether what we sort of wish were true. And we're going to find that it's probably not, right? Yeah, I cannot just take the derivative of the top and the derivative of the denominator separately. I just can't. So let's play with it to try to see that that's the case. The first one actually is the derivative, right? This is the answer. This is truly my answer, because I'm going to do it in sort of an order of operations. I'm actually going to divide f of x by g of x to start with, and then I'm going to take my derivative. So what is 4x to the 9th divided by x cubed? Right, 4x to the 6th. And what's the derivative of 4x to the 6th? Yep, 24x to the 5th. Lovely. That's the answer for real. Okay? I had the ability to simplify, so I did, and then I found my derivative. Now we're going to do the same thing we did before. We're going to take the derivative of the top and the bottom separately. So we've already done this once, but it was 36x to the 8th and 3x squared. Right, that's if I take the derivative of each of the individual pieces first. What will that give me? I like how you get to the heart of the issue. It is not the same answer. That is really the point, right? So what it actually is 12x to the 6th, right? And you're right, it is not the same answer, right? They're not equal. This is not a quotient rule, right? It doesn't work if I just take the derivative of the top and take the derivative of the bottom. But I'll warn you that you're going to be really tempted to do it, because it feels like what you should do, right? I mean, it kind of does. Same thing with the product rule. It feels like you should just be able to take the individual products. So let's do some examples of ones then. Or let's actually do let me tell you what the quotient rule is, and then we'll do some examples with the actual quotient rule. Okay, the quotient rule's numerator is the same as the product rule, but with subtraction in between instead of addition. Do you see that? Same as the product rule, but with subtraction. And then you have a denominator that is the denominator, original denominator squared. You might be looking at this and thinking, I have to have all these memorized by Friday, and you do. You do, that's true. I'd like to give you a mnemonic device on this one that you can think through if it's helpful to you. It's still what I think in my head every single time I do a quotient rule. And I've been doing calculus for a really long time because I did it my senior year of high school, so maybe just a little bit younger than you guys. And so it's stuck with me. So my calculus teacher said we're going to call the value on the top high, and we're going to call the value on the top bottom ho. And I've seen people call it low too. But it sounds more fun in a minute here when I use the word like ho on bottom. Okay, ho. Because watch. So we're going to take the derivative, And it goes Hody Hi minus Heidi Ho all over Ho Ho. Not joking. I still remember this to the day. I mean, obviously I'm teaching it to you. That's not necessarily why, but this is how I always think about quotient rules, even now, always. Because Hody Hi came from something that was a part of my childhood. Do you guys know what it came from? Heidi Ho. Do you guys know what Heidi Ho comes from?
Heidi Ho, Ranger Joe. It's on.
It is on Heidi Ho Ranger Joe. There's something else.
I have no idea.
Now you guys are going to have to go look for it on like Amazon Prime or Netflix or whatever it is. I know you're too young, but I will tell you my children have watched this series.
Oh wait, really? What is it?
It's a series. It's called Tool Time.
I've never heard of that.
It's called Tool Time. It's got, it's a comedy. It's funny. It's got Jonathan Taylor Thomas in it as a child. He's played a lot of things even as he's grown up a little bit. What's that guy's name? Oh, man, now I'm going to have to go looking it up after class or something and send it to y'all. It's funny. It's very funny. My kids thought it was absolutely hysterical. We watched it during quarantine. Like when we were all stuck in the house all day for every day. Yeah, it's hilarious, okay? So this is why it stuck with me, I'm quite sure, is because Heidi Ho is a phrase that I was very familiar with, okay? So we're going to practice this, and I'm going to do it with the one we just did, kind of like I did on the last one. So we're doing these functions right here, okay? And we're going to do them in this order. So I would have had 4x, was it to the 9th? And x cubed. Okay, so if I want to take the derivative of this, I take the bottom, that's the Hody Hi part, and I write the bottom there. So that's x cubed. D high means derivative of what's on top, the derivative of what's high. Okay, so that would have been my 4x to the 10th. 9th, 8th, what do I have, 8th? Forget my numbers when I'm doing with. I was thinking about my number before. Okay, 4x. Oh yeah, totally fine. This is what happens when you zoom in and zoom out. I hope that gets that. Here we go, 36x to the 8th. Do I have it right now? Okay, good. And then I have subtraction. So that's Hody Hi minus Heidi Ho. So Hi would be what's on top. That's the 4x to the 9th. D Ho would be the derivative of what's on bottom. So that's the 3x squared. All over the denominator. Whoops. X cubed squared. Okay. So we typically have a fair bit of cleanup when we work with quotient rules, sometimes more than others. This one's got a lot because there's just a lot of cleanup with these particular functions. But we typically have some cleanup to do. So on this one, I have 36x to the 11th. Does that look right? And then I have minus, and I have 12x to the 11th. And what's on bottom? Good. Y'all remember your order or your properties of exponents. Good. X to the 6th. All right, so I can combine the pieces on top. What's 36x to the 11th minus 12x to the 11th?
24x to the 11th.
Yep, 24x to the 11th. And if I divide 24x to the 11th by x to the 6th, 24x to the 5th. And that's what I said it was supposed to be over here, so that's good news, right? Yeah, we did it right. It matched. Okay, so this is the quotient rule. So we're going to do an example of one now where the quotient rule is actually necessary. There is nothing in your realm of the things that I've taught you so far that allows you to do this problem until now. It has to use the quotient rule. Just like that one with the cosine in it and whatever had to use the product rule. Okay? So we're going to take and find the derivative, whoops, it's t, of g. And we start with what? The bottom. And we rewrite it. 5t minus 3. And then what? The derivative of the top, which is 2t. Minus, and what's the top?
T squared.
Yeah, that's what comes next, t squared plus 4. And then times the derivative of the bottom, which is just a 5. And we divide by the denominator squared. We're going to clean up the numerator. But unless there's a factorization that cancels with something in the denominator, we don't ever multiply the denominator out. Okay, so the denominator is going to stay exactly like it is unless we have the ability to reduce it in some way. And multiplying it out is not going to be helpful in that anyway. Okay, so we're leaving the denominator as is, and we're going to clean up the numerator. So we have 2t distributing through to give me what? 10t squared minus 6t. And then I have the 5 distributing through and the negative, right? So keep that in mind. What will that give me? Good. I think I'm hearing all the pieces coming out. That's great. Minus 20. And my denominator is the same. Okay. Anything else I can clean up in the numerator? Yes. So I have 10t squared and negative 5t squared, so that's 5t squared. The other pieces, they don't work though, right? This is all over 5t minus 3 squared. Now occasionally, this will be able to simplify. This one doesn't, and let me tell you how you can know right away. You stand a chance because there's a 5t here, and you could factor the top and get a 5t at the beginning and a 1t, right? Like that would make sense if you tried to factor this. Agreed? Right? If you tried to factor this, one of them would in fact be 5t, and one of them would be t. But there's no way that this answer can have a 3 here. Why can I not have a 3 in that location?
Because 20 would be 5 and 4.
Right. 20 didn't have a factor of 3, right? So since 20 doesn't have a factor of 3, even if the numerator factors, which would be fine, I don't need to factor it because the only purpose in factoring would be to reduce with the denominator, and that can't happen on this problem. Which means after you visually check that that will not factor in a way to reduce, then you're finished. And you're done. It's probably worth noting that if you're doing the derivative gateway next week, you would just stop right here. Okay, no simplification, the one in boxed in red. It's a good question. If you simplify it and you simplify it right, I will not take any points off. But if you simplify it and you simplify it wrong, I will. You'll miss the problem. So it is in your best interest to not simplify just in case you were to make a mistake.
So I'm not going to remember the notes.
Well, it says on the top, do not
it does?
simplify. So you're welcome to highlight it.
So basically,
On
you
the
just
quiz.
want us to
like
use
write
the
it all over.
rules first and then
Yep.
stop.
It's just use the rules, apply the rules, and then stop. Apply the rules and then stop. And there will be 20 questions. It's the only thing we're going to do next Friday is just take that quiz. You'll be done early next Friday. When you come into my office, you'll have the ability to, like if you don't pass it with the 18 the first time, you'll have the ability to come in my office and repeat it for a week. Okay?
So-
Like all next week. Well, not next week, but the week after that quiz.
Will the instructions to not simplify be in big?
I think it says do not simplify in all caps.
Okay, that
And you're welcome, like I said, to highlight it if you have a highlighter.
because
Use
I
it with
really
you.
know I'm bad at
Circle it,
reading.
exclamation point. Yeah. Okay, let's do one more and then we're going to stop for today because it's a nice stopping spot. Okay, quotient rule again. We have sine of x over x cubed, and we're going to take the derivative. Let me use my black. Okay, where will we start?
Get the bottom times the
Mhm. The bottom times the derivative of the top. So what's the derivative of sine x? Good. Cosine of x. Then what?
The derivative of the bottom.
First I need
You need the top one and then the
minus, thank you. Shelby's right, yeah. Don't forget the sign. We want to be careful, especially because some of them have negatives and the product rule is positive. So we have a negative. And then what were we saying next? Okay, sine of x. Well, we can do it in whatever order. If you want to write sine of x first, you can. If you want to write the derivative at the bottom, you can first. It doesn't really matter because it's commutative. But 3x squared and sine of x. Those are the two pieces in some kind of order.
X cubed squared.
We saw that one a minute ago, didn't we? X cubed squared. Okay, so now I have x cubed cosine x minus 3x squared sine x over x to the 6th. So again, if we were on the gateway next Friday, you would stop here. But we can't stop where we are right now because there's still more that I can do to clean it up. This one actually I can clean up something else. What can I do?
You can,
Yeah, there's an x to the third, there's an x squared, and there's an x to the sixth, right? In every single term. Remember, terms are separated by addition and subtraction. They have 3 terms, 2 on top, 1 on bottom. They all divide by x squared because they have 2 x's in common, yeah. So I can eliminate 2 x's from each of them, making this one an x, cosine x. This one a 3 sine x, and the denominator would be
could you,
x to the 4th. Could you what?
could you like, do like, separate them?
You could. So if you were to take this and you were to rewrite it as 2 separate fractions,
Yeah.
like x cubed cosine of x
Then you could get rid of the other x.
over x to the 6th
Yeah.
and 3x squared sine x over x to the 6th, you could. If you simplified from there and you had the 2 separate fractions as your final answer, it would still be right. It would look a little different, but it would be right. You'd end up with a cosine of x over x cubed and a 3 sine x over x to the 4th. That's equivalent to what we have. It's just that if you were to try that at this point, like on the one you just did, and you did a common denominator, it would become what we just created. So they are equivalent, but they would both be correct and reduced as simplified. They would both be fine.
Both of them?
Yeah, both should be fine. Either of these are equivalent and they're both okay.
Because my brain wanted.
Your brain can do that and they'll be just fine. Okay, so we're going to stop there for today because we're going to move into the other part with trig functions next time. And then we will not only finish trig functions next time with their derivative stuff, we will also move into a little bit of the chain rule. Okay? So have a good weekend.